Hey students, I wanted to work a problem for you that I saw on one of my favorite YouTube channels for math. And I'll link to the original video where I saw this problem worked to give him credit for it. But I wanted to work this problem here. And the reason why I found this one to be quite interesting is because my AP Calc students, they are starting to do what's called U-substitution with integration. And U-substitution with calculus doing antiderivatives or integration is a technique that helps you take a more complex function and simplify it so that you could then take the antiderivative much more easily. It's really a way for us to undo something called the chain rule of a derivative when you're taking an antiderivative. But I wanted to show students that may be familiar with this thing called U-substitution in calculus and show you that U-substitution is not just for calculus problems. It actually can be used to help you solve a problem algebraically, and this is an example of such a problem. When you take a look at this, you've got two trinomials that are being multiplied and it's set equal to 5. Now your first inclination may be to go ahead and expand this, that is to multiply the two trinomials together. But as you can imagine, that's going to create a monstrosity, right? It's going to be a fourth degree polynomial. You could maybe try to solve it by bringing this 5 over and then perhaps refactoring it maybe and using some technique such as long division or synthetic division. But that's not going to be a good option. The one thing that I noticed though about these two trinomials is they do share the first two terms. So what I'm going to do, and those of you that have done U-substitution in calculus, this will make sense. I'm going to use the variable u to represent those two terms, x squared plus 6x. Now what I'm going to do is I'm going to rewrite this problem substituting u in for those two terms. And there we go. So you can see that what this does is replacing the two terms x squared plus 6x with u, it makes a more manageable problem that I could work from there as a quadratic. So what I'm going to do is I am going to go ahead and multiply and expand the product of those two binomials out, which would give me that. And then I'll bring that 5 over and I'm going to proceed to solve this as a quadratic, like that. Now what I'll do is I can recognize that this is a factorable quadratic trinomial. So I could then factor it into those two factors. And then that gives me two solutions for u, right? You would set each one of those factors equal to 0, and it gives you two values of u. But of course, we're not interested in what u is because that wasn't even a variable of the original problem. We're really interested in knowing what x is. So then what I'm going to do is I'm going to go back to the original definition for u, and I am going to set the x squared plus 6x up here equal to each one of these and create two other problems. So this would be 4 is equal to x squared plus 6x. This one would be negative 2 is equal to x squared plus 6x. All I'm doing is I'm taking these values for u that I just discovered through this process of factoring this quadratic trinomial, and I'm putting them back in for u up here. Now what I will do is I'm going to have to solve both of these quadratics separately so that I can figure out what the x solution is to our original problem. So what I'll do is I will rewrite this as x squared plus 6x minus 4 equals 0. This one will be x squared plus 6x plus 2 equals 0. And I'll solve these separately. Now what I'm going to do, I could pretty quickly see that this is not factorable and neither is this one. So I'm going to use completing the square because I have a 1 coefficient and this is an even number. So it makes that pretty simple instead of the quadratic formula. So what I'm going to do is I'm going to move that 4, negative 4, back over as 4. I will take half of this coefficient and square it, which gives me 9. And then I will add 9 to the other side to compensate for that. And that makes this a perfect square binomial. And then I have to square root both sides. This will give me a plus or minus root 13. And therefore, when I subtract the 3, I get two solutions here. Negative 3 plus or minus the square root of 13. I will do the same technique here. I'm going to move that 2 back over as a negative 2. Take half of this, which is 3, and square it. It gives me plus 9. I put a plus 9 over here. I will factor this as a perfect squared binomial, and that's a 7. I will square root both sides, giving me plus or minus the square root of 7, and then subtract 3, and there we go. So what it turns out is that this original problem, which we knew if we had multiplied it out was going to be a 4th degree polynomial. So no surprise, there are 4 solutions to it. And those are the 4 solutions. Well, you say, well, there's only 2 solutions. No, there's 4 because this gives me 2 solutions here. Negative 3 plus root 13, negative 3 minus root 13. Over here, negative 3 plus root 7, negative 3 minus root 7. So I just wanted to show you this example, students, that U-substitution is not just a calculus concept. It's something that could help us solve more complicated algebra problems. It is true that this was a convenient problem to use U-substitution with for the fact that these 2 terms up here were exactly identical. So it made it a natural U-substitution problem. If those 2 didn't match, then U-sub probably would not be something that I would even really be considering. Okay, I hope you found that useful. If you did find it helpful, give me a like and subscribe to my channel. I do come out with content every week. Each Sunday night at 8 p.m. I am live, and I take math questions from my students and also give you an interesting topic at the very beginning. So join me Sunday nights at 8 o'clock. Take care. See you in the next video.